Dear students, we know that the rotating magnetic field in the air gap of an induction machine cuts the stator as well as the rotor windings and hence induces EMF in both the windings. In our last lecture, we derived expressions for the EMFs induced in the stator and rotor windings. The EMF induced per phase of the stator is given by induced E1 equal to 4.44 F1 phi N1 kW1, where we know that F1 is the frequency of the stator induced EMF, which is equal to the frequency of the supply. Phi is the flux per pole of the rotating magnetic field, and N1 is the number of series turns per phase of stator, and kW1 is the stator winding factor. The EMF induced per phase of rotor is given by E2 equal to 4.44 F2 phi N2 kW2, where F2 is the frequency of the rotor induced EMF, which we have seen is given in terms of the stator induced EMF, frequency of the stator induced EMF as S times F1. Phi is again the flux per pole of the rotating magnetic field, because it is the same field linking both the stator and rotor windings. N2 is the number of series turns per phase of the rotor, and kW2 is the rotor winding factor. One important thing to note from these expressions is that the frequency of the rotor induced EMF, it is a function of the rotor self S, which is given by omega S minus omega R by omega S. Omega S is the speed of the rotating magnetic field, synchronous speed, which is a constant. Therefore, S depends upon the rotor speed, and hence the frequency of the rotor induced EMF is a function of the rotor speed. This depends upon speed of the rotor, and therefore if a constant frequency is supply is applied to the stator, and if the rotor is rotated at different speeds, the EMF induced in the rotor will have different frequencies. To illustrate this, we'll today solve a couple of numerical problems. So let me read the first numerical problem. A three-phase 4-pole 50 Hz slip ring induction motor has 420 and 240 stator and rotor turns. The magnitude of the flux per pole is 30 milliweber. The winding factor for both the stator and rotor is 0.96. Calculate the frequency and magnitude of the per phase EMFs in the stator and rotor windings when the rotor is standstill, rotating in the direction of the rotating magnetic field at a speed of 1440 rpm and rotating opposite to the rotating magnetic field at a speed of 1440 rpm. So let's solve this problem. Let's first write down the data that has been provided in this problem. It's a 3-phase machine with 4 poles. F frequency is 50 Hz. The total number of turns in the stator is given as 420 and that in the rotor is 240. Therefore, we can calculate from this number of turns per phase of stator. N1, it will be 420 by 3, which is 140, and N2, the number of series turns per phase of rotor will be 240 by 3, 80. The flux per pole phi is given as 30 milliwebers, that is 30 milliweber, which can be written as 0.03 Weber. And the winding factor for the stator and rotor is equal. Kw1 will be equal to Kw2, 0.96. We have to calculate the frequency and the magnitude of the EMF per phase of stator and rotor. Now, as far as the EMF induced in the stator is concerned, we see that from the expressions we can see that the EMF induced is independent of the rotor speed, and therefore it will be same in all the 3 cases. It will not be affected by the speed of the rotor. Let's therefore proceed to calculate the EMF induced per phase of the stator. First, the frequency F1 will be equal to F, which will be equal to 50 Hz. And E1, the EMF induced per phase, will be given by 4.44 F1 phi N1 Kw1. So let's put the values in this equation. 4.44 into 50 into 0.03 into N1 is 140 into Kw1 is 0.96, which equals 895.104 volts. So it will be same in all the 3 cases, the frequency as well as the EMF induced. Now let's calculate the EMF induced in the rotor. It will depend upon the rotor speed. Therefore, let's consider case A when the rotor is stationary. That means NR will be equal to 0. Therefore, as you can see that the slip S, which is NS minus NR divided by NS, it will be equal to 1. NR is 0, so it will be equal to 1. Therefore, F2, the frequency of the rotor induced EMF, will be equal to SF1 which is equal to F1, same as the stator frequency. And then E2 will be given by 4.44 F2 phi N2 kW2, which will be equal to 4.44 into F2 is again 50 into 0.03 into N2 is 80 into, then we have kW2 as 0.96. This comes out to be equal to 511.45 volts. Then let's consider the second case, where the rotor is rotating in the direction of the rotating magnetic field at a speed of 1440 rpm. That is, NR is given as 1440 in the direction of rotating magnetic field. Now first we need to calculate self, and for that we'll require NS. Let's calculate therefore NS. NS is equal to, it's in RPM of course, therefore it will be 120 F upon P. We have already derived this expression, which will be equal to 120 into 50 by P. It is a 4-pole machine, 4, which will be equal to 6000 by 4, 1500 rpm. So for a 50 hertz supply for a 4-pole machine, the synchronous speed is 1500 rpm. And here NR, here S will be equal to NS minus NR by NS, which will be equal to 1500 minus 1440 divided by 1500, which equals 0.04, which is 4%. And you should remember that under normal operating conditions, the slip of an induction motor is very small. It is of the order of 2 to 5%. Here it is 4%. And with this slip, the frequency of the rotor induced EMF F2 will be equal to SF1, which will be 0.04 into 50, which is equal to 2 Hertz. We see that the frequency of the rotor induced EMF is very small. It is near to DC. Then E2 therefore can be calculated. It is 4.44 F2 phi N2 kW2, and if we put the values here, 4.44 into F2 is now 2, flux per pole is 0.03 into N2 is same, which is 80 into 0.96, and this equals E2 is of the order of 20.5 volts. So we see that since the speed of the motor is quite high, it is close to synchronous speed. Therefore, the relative speed between the rotating magnetic field and the rotor is small, which corresponds to a small value of slip. The frequency of the induced EMF is small, and also the magnitude of the induced EMF is quite small. Now let's consider the third case, part C of the problem. The rotor is rotating opposite to the direction of the rotating magnetic field at a speed of 1440 rpm. 1440 rpm. It is rotating in direction opposite to the rotating magnetic field. Therefore, we can write NR as negative minus 1440 rpm, and hence the slip will be given by ns minus nr by ns, which is equal to 1500 minus 1440, that is plus 1440 by 1500, which is equal to 1.96, and therefore with this value of slip, f2 will be equal to sf1, which will be equal to 1.96 into 50, which is equal to 98 hertz. So we see that when the rotor is rotating in a direction opposite to the rotating magnetic field, the frequency of the rotor induced EMF is higher than the supply frequency, and since it rotates at a quite large speed, therefore the frequency is also quite large, and the EMF induced in the rotor will be given by 4.44 f2 phi n2 kw2, which will be equal to 4.44 into 98 into 0.03 into n2 is 80 into 0.96, which is equal to 1003.17 volts. So you can see that the frequency as well as the magnitude of the rotor induced EMF is quite large in this case. So let's solve another problem. I'll read the second problem. The stator of a 4-pole 50 Hz induction motor is supplied from a 3-phase 50 Hz supply. The slip rings of the machine are open circuited. It is desired that the frequency of the voltage across the slip rings be 50 Hz or 75 Hz, 100 Hz or 25 Hz. Find the speed and direction of the rotor to obtain this. So we can see that in this problem we have specified the frequency of the rotor induced EMF, and in order to achieve the desired frequency across the slip rings, we have to find the corresponding speed at which the rotor has to be rotated. So let's proceed to solve this problem. Solution. Let's first write down the data that has been provided. We are given the number of poles is 4, F is 50 Hz. The slip rings of the machine are open circuited. Now we are given, let's do for case 1, part A. F2 has to be equal to 50 Hz. Now F1, as we know, is equal to F, which is also 50 Hz. Therefore slip can easily be calculated. S will be equal to, because we know that F2 is equal to S times F1, slip will be equal to F2 by F1, which in this case will be equal to 1. And hence we can find the speed of the rotor in terms of slip. As we know, it is given by ns minus nr by ns. From this we can also see that nr will be equal to 1 minus s times ns. We could write this as 1 minus ns by nr, from which we can write this expression also. Therefore in this case nr will be equal to 1 minus 1 times ns, which will be equal to 0 times ns, that is 0. That means the rotor has to be kept stand still. We already know it, that when the rotor is stand still, the slip is equal to 1, and the frequency of the rotor induced EMF will be same as the frequency of the stator induced EMF. part B, it is desired that the frequency now be 75 Hertz. F is given as F2 is given as 75 Hertz, and therefore S will be equal to F2 upon F1, which will be 75 by 50, which will be equal to 1.5, and hence NR will be equal to 1 minus S times NS, which is equal to 1 minus 1.5 into NS for this machine. We have yet not calculated it, so let's first calculate NS also. NS will be equal to 120 F by P, which is equal to 120 into frequency here is 50 by P is 4. We have already said that it is equal to 1500 RPM. So with this value of NS, therefore this will be equal to minus 0.5 into 1500, which is equal to minus 750 RPM. So a negative rotor speed means that the rotor will be rotating in a direction opposite to the direction of the rotating magnetic field at a speed of 750 RPM. So we can write it here. Rotor will be rotating at 750 RPM opposite to the rotating magnetic field. Then part C of this problem, the frequency has to be 100 Hertz. F2 now has to be 100 Hertz. It has to be done in a similar way. We can calculate S will be equal to F2 upon F1, which will be 100 by 50, which is equal to 2. Therefore NR will be equal to 1 minus S times NS, which here in this case comes out to be equal to minus NS with 2. So NR therefore will be equal to minus 1500 RPM. Therefore the rotor will be rotating at a speed of 1500 RPM opposite to the rotating magnetic field. And then for part D, F2 is equal to 25 Hertz. Now the frequency desired across the self rings is lesser than the frequency of the applied voltage, and quite obviously the rotor must be rotated in the direction of the rotating magnetic field at a speed lesser than synchronous speed. And let's try to find it out. S will be equal to F2 upon F1, which will be equal to 25 by 50, which is 0.5, and therefore NR will be equal to 1 minus S times NS, which will be 0.5 into 750 RPM, which will be equal to 1 minus 0.5 into 1500, which is 0.5 into 1500, which is equal to 750. RPM. So the rotor must be rotating in the direction of rotating magnetic field at a speed of 750 RPM. So we'll stop here. In the next class we'll discuss the development of torque in an induction motor. Thank you.